This is for a two-sided case. So maybe we can look at this. This is also done similarly in the continuous time case. So we have these two-sided exponentials that are either decreasing or increasing depending on the value of b. Okay? So for two-sided signals, right, if you want to compute the z transform, what you can do is that you can split it into a left-sided signal plus a right-sided signal. Okay? So for this case here, xn equal to b to the power absolute n, you can split this into b to the power n times un plus b to the minus n times u minus n minus 1. Okay. So this is probably a little bit different from the continuous time case because the indices are discrete. So you have to be clear about which indices are included in the right side and which ones are on the left side. So basically, we take all indices from 0 to infinity as the right side, and all indices from minus 1 to minus infinity as the left side signal. Okay? Now, to utilize the results from example 10.1 and 10.2, we want to write it in that form. So for convenience, let me write this as 1 over b to the power n u minus n minus 1. Okay? And the reason I want to write it in this form is so that it is consistent with this form here. Okay. Okay. So then by directly applying the results in examples 10.1 and 10.2, you have the first term equal to z over z minus b minus the second term, which is z over z minus 1 over b. Okay? And the region of convergence for this is z greater than b. And the region of convergence here is z less than 1 over b. Okay. So you can see here that if you have b that is greater than 1, then these two regions actually do not overlap, right? So there is no common region of convergence if b is greater than 1. Okay? So if b is greater than 1, this means that there is no z, the z transform does not exist for any choice of z. Okay. And this is intuitive, right? Because if b is greater than 1, then your signal looks like this. You're exponentially increasing on both sides. So if you apply an exponential that decreases in this direction, it suppresses this part but not this part. If you take the exponential decreasing towards the left-hand side, then you decrease this part but not this part. Okay, so no choice of z is good enough to give you a convergence in the z transform. Okay, but if b is between 0 and 1, then the ROC is b less than z less than 1 over b. Okay. So hence, if you combine them together, you have x of z equal to b squared minus 1 over b times z over z minus b, z minus 1 over b. Okay? And the ROC is z between b and 1 over b. So here, I'm just combining these two terms together. Okay. So you can see that there is a 0 at 0 and two poles, one at b and one at 1 over b. Okay. Okay. So on the next page, what we have is just illustrations on the complex plane of these two cases. Okay. So when b is greater than 1, then this region of convergence, okay, is this region exterior of this circle that has radius greater than 1. And this second term has region of convergence that is this interior with radius less than 1. So the intersection between these two gives you an empty set, right? There's no common ROC. But if you instead, okay, so this is for b greater than 1, right? Now if you instead choose b that is between 0 and 1, then the first term gives you this, the second term gives you this, and the intersection of the two gives you a ring from b to 1 over b. Okay? Okay. Now these are for general left-sided, right-sided, and two-sided signals. Okay. So these previous properties are for general right-sided, left-sided, and two-sided signals. Okay. Now similar to the continuous time case, we can also look specifically at the case where x of z is rational. Okay. So if x of z is rational, then it further guarantees that these ROCs are bounded by the poles. Okay, they are bounded by the poles. Okay, so right, if x of z is rational and is a right-sided signal, then we already know that in the general case, the ROC is this exterior of a circle. But what this tells you is that if it is rational, then it must be outside the outermost pole. Okay? So if you have something like this, right? So suppose that this is the unit circle. If you have a pole here, right? And you know that it is right-sided and rational, then your ROC must be something like this. Okay? But what it cannot be something like this. Okay? It has to be extended to a pole. Okay? So this is the same as in the continuous time case as well. Okay. So vice versa, if you're looking at a rational and left-sided signal, then it must be an interior extended to the pole. Okay? Right. So if you have a rational x of z, there are only three possibilities of the ROC. One is that it is the exterior of the outermost pole, it is the interior of the innermost pole, or that it is a ring in between two poles. Okay? Okay. All right. So let's look at this example. Okay. So you can see all of these things keep on repeating, right? All these examples appeared in the previous chapter as well. Okay. So suppose that we have x of z that looks like this, right? This is rational, okay? And if you want to find the poles and zeros, you want to write it into polynomials of z in both the numerator and denominator. Okay. So you can do this by just multiplying both numerator and denominator by z squared. So you have z squared over z minus 1 over 3 and z minus 2. Okay. So you have two zeros, two poles, one at 1 over 3 and one at 2. Okay. So two zeros at the origin, one pole at 1 over 3, and one pole at 2. Okay. So in this case, you have three choices of the ROC. It can either be, the exterior, okay, outside of the outermost pole, the interior inside of the innermost pole, or that it is some ring, okay, between the two poles. Okay. Right. Now, furthermore, you can see here that the Fourier transform exists only in this case, right? Because only in this case will it include the unit circle. Okay. So in this case, the Fourier transform exists. Okay. Right, so we've talked about what is a Z transform, right? These basic Z transforms given for the right-sided exponential and the left-sided exponential. And by combining variations of these left and right-sided exponentials, you can get x of z that are these general rational forms. Okay. Right. Now, the next question is naturally, if you are given a Z transform, how do you find the original time domain signal? Okay. So this is the inverse Z transform. Okay. So following the same logic as we did in the continuous time case, we can obtain the inverse Z transform. Okay. So I had typos in the notes, right? There should be an R in these places. Okay. Okay, so if you recall, for Z transform, if you let Z be equal to R times e to the j omega, the Z transform can be written in this form, which is basically the discrete time Fourier transform of x of n times r to the minus n. Okay? So this Z transform you can view as the Fourier transform of this weighted sequence x of n, okay, times r to the minus n. So given this Z transform, you can compute x of n times r to the minus n by taking the inverse Fourier transform, which is defined as 1 over 2 pi, the integral of x r e to the j omega times e to the j omega n d omega, integrating over one period 2 pi. Okay? So if you take r to the minus n and multiply it inside here, you get this. Okay? So I'm just multiplying this inside here, so this becomes this. Okay. So by a change of variable, where you just, okay, by a change of variable where you set z equal to r e to the j omega, okay, you can then obtain the z transform, okay, the z transform of x of z, okay, given in this form here. Okay. Now notice that now we're taking this integral, okay, over a contour, okay, around the circle described by this z equal to r times e to the j omega in the region of convergence. Okay. So if you look at this, right, we're taking an integral over r times e to the j omega for omega that varies from 0 to 2 pi. So this is basically a circle with radius r, right, with face going from 0 to 2 pi, right? This is one circle, okay? So if you do a change of variable, this is then this contour integral around this circle, okay, described by this. Okay. So again, computing a contour integral is not that straightforward, right? So in practice, to find the inverse z transform, what we do is that we try to identify patterns in your z transform that are of known, z transform identities, right? Some common z transforms that we know, okay? So an example is z transforms taking on this rational form, okay? So when you see a z transform like this, right, one thing that you naturally think of doing is to decompose it using partial fraction expansion, okay? So indeed, if you use partial fraction expansion, you can split this up. Okay, so by partial fraction expansion, you can split this into 1 over 1 minus 1 over 4 z inverse plus 2 over 1 minus 1 over 3 z inverse. Okay. So again, by partial fraction, right? Okay. So by partial fraction expansion, you get x of z in this form. And we know how to deal with this form, right? So this is in the form of examples 10.1 and 10.2, okay? So the only thing remaining that we need to determine is the region of convergence. Now, since the overall transform has a region of convergence that is the exterior of a circle, this means that the ROC for both of them must also be exteriors of the circle, okay? So this thing here has ROC that is greater than 1 over 4, and this we get z that is greater than 1 over 3. Okay. So if you do if you apply example 10.1, you get xn that is 1 over 4 to the power n, okay, plus 2 times 1 over 3 to the power n times the unit step function. Okay. Now this is for the case when the region of convergence is the exterior of a circle. So if this is an exterior, then both of these have ROC that are exteriors of a circle, and therefore x of n corresponds to a right-sided sequence. Now, obviously, if you choose a different ROC, then this time domain signal would be different, right? So two other cases is for z corresponding to this ring between the two poles, or the interior of the innermost pole, okay? So for this case, xn is a left-sided signal, and for this case, it is a two-sided signal, okay? Right. So this corresponds to a two-sided signal. This corresponds to left-sided.